Hello everyone, how is everyone doing? I just want to present a very critical case of my research when I was working in the OEM before starting this whole startup called 2 to 4 Wheels. There was like an application that we were working on for electric car companies, and most of the electric vehicles, when people buy in like critical environment conditions, critical environment meaning like environment or ambient temps being too hot or too cold, we always have an issue of range anxiety. And the reason being like whenever like a electric vehicle is run in like an environment which is like negative 20 degrees Celsius, like the range of the car that the manufacturer promises, let's say it's 250 miles per charge, per complete or full charge, reduces by 20 to 30% to like maybe 180 miles per charge. So we try to incorporate new engineering ways to extend the vehicle range and battery life. And there are like a few um, options that we do. Like there are a lot of algorithms that we select, and then one of the algorithm out of the 100 different algorithms, or like a lot 100 different permutations and combinations that we use, is a heat pump. Now, how a heat pump works in this presentation, I'll be covering or touching upon like how heat pump, basically the industrial application of heat pump works, like the passive and active heating and cooling. Then we'll also touch base on the scheduled cabin conditioning, the post cabin conditioning. The vehicle is kept running even after like a person exits the car, so that like if it's a coffee break, for example, so we don't want the car to shut down and cool itself, so we keep it running for a while, so it's more comfortable for the, the driver to come back and feel like the comfort of the localized ambient temperature that we have maintained inside a car. Let's say if the ambient outside is negative 20. We also do an algorithm of driver detect conditioning. So let's say if like a person leaves the car at 72 degrees Fahrenheit, the ambient is only 0 degrees. So when he comes back, like we'll see that the driver is not in the car, we'll shut the conditioning off. And then through the cameras around the car, we monitor, okay, now that he's coming back, we'll turn the conditioning on. There are a lot of different permutations, combinations going on, but we'll start with like very basic thing, which is a heat pump, and then we'll eventually I'll cover the other topics as well. So everybody here has heard about the Tesla Octo pump, right? Now, what is an Octo pump? I'll start the explanation. When we do the heat pump, we just have to think about only the two laws in thermodynamics. I'll not go into the entropy and enthalpy laws, but like we just consider the zeroth law and the first law. Now, zeroth law is basically whenever like a, a component A is in thermal equilibrium with a component B, so they essentially are in thermal equilibrium with it by themselves. Like then A and C also become in thermal equilibrium. And what the first law says, like one of the the explanation of first law is, so energy can never be created nor destroyed. It can just change from, or it can just transform from one energy source form to another. So what that means is like, let's say if we are using a mechanical energy, so like the full mechanical energy is not delivered at the final output. There is some loss, and that loss is heat energy. But like when you combine the heat and the efficiency of, let's say, that mechanical energy, then that combines to like the input source. So like let's say if we are applying chemical energy or like electric energy to get some gears driven. So like the gears are only like 92% efficient. So we have that 8%, we call it as a loss. But that loss is just like a heat energy going out from the system. All right, let's start with the overview of the heat pump. Now, every conventional vehicle that you drive today that has an engine has a heat pump. This is just the air conditioner of your car. Um, Now, like, so the what is an air conditioner? It's a device or in a vehicle which transfers heat from one form to another by using different components. Like we have an evaporator, a condenser, and like we have a compressor, and then we recirculate the refrigerant, which changes form like from gaseous to liquid, liquid being chiller form, gaseous being where it's hot now. So the issue that we see is that in a BEV or in an electric vehicle, we do not have like a free heat source. The free heat source being like, let's say for heating, we don't have an engine that can reject heat and then we can take that heat and put that into the cabin. So we have to source something, and that something is like basically if we see there's a heat rejected from some other components, we try to capture that. The only way to cool or heat the cabin in a BEV is by using the energy from the high voltage traction battery. And what happens is like when we start using the energy from high voltage traction battery, we also start depleting the battery. So once we start depleting the battery, that's the scenario that causes the range anxiety, right? Because you are using the heat like for a negative 20 degrees cold morning, you will be heating more, like you will be needing more heat in the cabin and you will be using your heater much more than your than on a day when the outside ambient temperature is only 25 degrees Celsius, right? So exactly like in your home also you might have seen like if it's a cold environment, like your heating bills get high. Same thing here, the heating bill is actually taken care by the high voltage battery. So what we do is like we do a cabin passive heating. We prioritize this always if the battery is not into the critical region, and then we also do battery passive heating. I'll just touch heating topic. Now Tesla, what it does, they call it as a lousy mode in which they heat or they don't have a heater, right? So they just start running all the power electronic devices into like the most inefficient way to heat the coolant inside the car, and then that coolant is passed through the high like the through the cabin loop, and then a heater core is used and a fan is used to blow through the heater core and take that heat into the cabin. So that's like a Tesla strategy, Octo Pump and the lousy mode. But like the other OEMs have went or incorporate even better strategy, and I'll touch base over here.
Let's start with the Octo Valve, what Tesla uses, which is very ingenious. So the Octo Valve has like four separate inputs and four separate outputs going into four separate loops in the car. The major loops being AC air conditioning loop, this red being the heating of the cabin loop, green being the power electronics. I don't have a yellow color, but let's mark this as orange. Orange being the battery loop. We have a high voltage traction battery. So how the octovalve works, it's like one valve that actually monitors the flow from everywhere. Basically, we have to do a heat and mass transfer. So let's say now this power electronics loop has enough energy, QPE, to heat the cabin. So the octovalve will start the flow from power electronics and take that flow to the cabin, and then we have to basically, so whatever the rejected heat or in the coolant is left, that goes back into the power electronics loop. We cannot segregate the two loops once the octo valve is open. Same thing, let's say power electronics loop has heat, battery loop needs that. We open the battery valve side and we start proportionating the flow here. Usually it's the vice versa, battery rejects a lot of heat when like the heaters use that, so we try to take the heat off of the coolant without running the chiller. And now what the octovalve does, remember I was talking about the zeroth law of thermodynamics. Let's say this power electronics loop has 100 kilojoules of energy that was rejected by all the power electronics. The high temp cabin loop needed 50. So basically we start flowing that 50 kilojoules to the power electronics. or sorry, to the cabin loop. And then let's say this needs 30 kilojoules. So we start flowing that 30 kilojoules to the battery loop. So what that does is, like, let's say now this and this become in thermal equilibrium 100, and we are maintaining this sending 50 kilojoules, and then this also becomes in thermal equilibrium, let's say with the power electronics. So that implies that these two are also in thermal equilibrium, because this is taking 30 kilojoules, this is taking 50, and the rest is going through the radiator.
So let's see, like just for the starter, the few um, like abbreviations that I use. It's PECOT is power electronics coolant temp outlet sensor. Let me start a marker here. Give me just a second. So if you look at it, so power electronic coolant outlet temperature sensor will be right here. Then we have a TPEI, which is the thermistor power electronics inlet, which is like this is power electronics, which is like the inverter and the motor and the OBCN and the APM module in the power electronics field. So this convention that you see here, like green line, is like an industry standard. Like the power electronics coolant loop is actually shown in green. Then we have AC, which is blue, which is very normal in industry. The yellow loop that I show here, the yellow line that you see is for the battery cooling and heating loop. And then the red is basically the heating loop of the cabin. So THO is the thermistor heater outlet, which is right here. Okay, let's start. Like first, let me give you some details. So when I'm doing my research, or when I was doing my research in this thermodynamics topic, so the power electronics basically are the best working, or like conserve their life when they are operated between -5 to 75. So that includes your AC bus bars, your DC bus bars, your bulk capacitors, your MOSFETs or IGBT, whichever gate is being used in the control board. That will also include the super caps. That can include like any devices like the junctions where you hold the MOSFETs, the IGBTs, and then for us, the battery has the optimum operating range between 0 and 45 degrees. Anything above 45 degrees, we start to derate the performance of the motor so that we are not taking that much current from the battery pack, from the high voltage battery, traction battery pack. And then anything above 55 is basically a zone for us where we can see some fire also catching in the battery packs. Okay, so I think that is shared now. So what happens is, like, let's say when you are in a cold morning, the ambient being -20. So this is something that we called active conditioning for the cabin. So as soon as the driver comes in, or like if we detect that the car is plugged in to an outlet, so we start using the energy from the outlet or from the high voltage battery and start running the heater to heat the cabin. So let's say the outside ambient was -20, the inside of the car will be still around -18. So we start running the heater. And the reason is because this entire power electronics loop is also cold enough. So we won't have any energy and heat and mass transfer happening between the power electronics loop and the heating loop of the cabin. So these are isolated, like both loops are running by themselves. We are trying to heat the cabin so that when the driver walks in, he feels comfortable to drive the car. Now, let's say we start driving the car for a little while, and then we see that there's some heat starting to get rejected in the coolant. Let's say the coolant was flowing as -20. Now, like we have some heat rejected by the motor, the inverter, the all the devices in the inverter, like the active and the passive, like I was telling you, AC bus bar, DC bus bar, then the gates and or the MOSFETs, IGBTs, whatever you want to say. It's technically a gate, like it's just the material difference. The junction, the copper, like the copper bars, so they start rejecting heat, and then this coolant starts to heat up. but we are still flowing this coolant through the, we are actually bypassing the radiator because the coolant is not hot enough. So we don't want to like start running the fan and run the coolant through the radiator. So we start heating the coolant as fast as possible. And then eventually we see that the coolant has started to heat up. Let's say the coolant from negative 10 went to like plus 10. So at that particular point, we calculate the Q, the energy needed in this loop to heat the cabin. And we also calculate the Q, the energy that this loop can provide. So let's say at this particular moment, the energy needed for the cabin is 100 kilojoules, for example. And then this loop can only provide 50 kilojoules, very layman term. So we open this proportionating valve right here and we start sending the coolant through the heating loop of the cabin. So at this point, like we still needed 100 kilojoules, but we are only getting 50. So that's still a bounty for us. The reason being, then we can turn this heater down to only 50% of its operating power. So let's say if this heater was 10 kilowatts, we can turn it down to only 5 kilowatt usage. And that starts conserving our high voltage battery. So that's a plus plus for us because now we are like trying to increase the range. And mind you, this heating of the power electronics loop and the heating of this battery loop actually happens really quick because there's a lot of heat that gets ejected into the coolant. So when this is the zone when we need 100 kilojoules and we are only getting 50 from the power electronics loop, we start calling this zone as active plus passive conditioning for the cabin because we have part active heating and part passive heating. Now our goal is to achieve full passive heating so that we basically cut this heater usage down and then we are not using the high voltage traction battery to run this 10 kilowatts or whatever power on the heater so that we can use this high voltage traction battery only to extend the range of the car so that we are negating the range anxiety in a person. So let's say now we are running the vehicle again and again. Like so, let's say now we have started. We are running the car. We are in like 5 minutes or 10 minutes of driving. I don't want to share like exact numbers because these can be very closely monitored by each and every manufacturer. So let's say 10 minutes of driving. Now this heat ejected in the power electronics loop is actually 100 kilojoules, and this is what we need inside the cabin. So then we shut this heater off completely, and this proportionating valve is open 100%, and all the cooling is flown through the power electronics and from the heater. So we run the fan right here, and that heat is taken from the coolant and dumped into the cabin. There will be a point when like heat needed in the cabin is less because we are also heating up like from negative 20 to 0 to 10 to 20, and then let's say 15, 20 because you're wearing uh, clothes that are made for the colder climates. At 15 degree, you might not need enough heating, so that's called a pseudo zone where like we see, okay, now we can shut this at 15 degree and like we can completely use the power electronics loop rejected heat to heat the cabin. And this zone, when we are using zero heater, is called like a completely passive heating of the cabin. So that now saves us a lot of energy and lot of usage of the battery to run the heater. This is the algorithm that I just explained you guys where like we calculate the Q from the high temp loop and we send it to the power electronics loop and vice versa. And then we see how much heat the power electronics loop have and then we based on that we calculate our logic to open the proportionating valve.
So I was talking about the proportionating valve. Um, we were using three different proportionating valves. There was like one proportionating valve here. Let me just use black for the valves. There was one proportionating valve here, and then there was a proportionating valve for the chiller, or we can say the chiller exchange shut-off valve, we call it, or the exchange valve. So again, like Octo Valve being more complex, OEMs have started to use the proportionating valve, but the exact principle is the same. So let's say this needs 50 kilojoules, this has 100 kilojoules. So we just proportionate the flow 50% from this power electronics loop to the cabin loop.
Okay, so next I'll move to the battery thermal management. Now, battery is again similar to how we do the cabin management, which is active, passive, and hybrid. Hybrid meaning active plus passive. So let's say if it's a cold environment, we'll turn the heater on in the battery loop. And then eventually, if we see enough heat getting rejected in this power electronics, we'll open the proportionating valve here. We'll let all this coolant flow through the battery pack so that we can negate the usage or eliminate the usage of this heater, battery heater, we call it. And then battery itself also rejects a lot of heat because each cell, whenever like it's giving out energy to power electronics or like to the motor, to the inverter, is actually rejecting a lot of heat which goes into the coolant, and then we start circulating that by itself. And then let's say if the heat in this circuit is like 200 kilojoules, so we want to reject that heat into the bigger power electronics loop or like the cabin, or like we also start cooling the coolant down through the low temperature radiator. So it's exactly the same logic I was telling you guys for the heat pump in the cabin. We do the same logic for the heat pump in the battery. Eventually, like when let's say the heat is much higher than we need to make the battery environment in this comfortable zone of like 0 to let's say 35 degrees Celsius. So we stop running the heater and we start just maintaining the temperature of the coolant so that we are in this optimum zone of this. Again, this is like the same algorithm where we calculate the heat rejected or heat needed by the battery management system when we are in negative 30 to 0 degree. And then similarly, we keep on going down and eventually we decide, okay, how much cooling, how much heating we need, whether we should turn the heater off, whether we need partial heating from the heater. But like eventually for the battery, because the cells are ejecting so much heat, so we attain that comfortable zone pretty quick and we just try to monitor the temperature of the coolant. Okay, so how we decide this is like if cabin needs heating, for sure cabin has the priority because we first target the customers. And like every time when the battery is in a critical zone, let's say critical zone is like negative 30 to 0 for the battery pack, and also like above 45, we will target the battery conditioning first. So those are the two disclaimers here. Like anything when the battery is outside of the critical zone, cabin becomes a priority for us because customer becomes the priority. Customer is always the priority. The driver should be in the comfortable environment. But in case the battery is in the critical zone, we don't want any fire to happen or we don't want like the range automatically to suppress from the battery. So we give battery the priority.
I think I'll have a lot more research topics to discuss with you guys. Thanks for watching the video. If you like the video, hit the like button and also subscribe to our channel because this is like 15 years of my research and now I'm doing only the automotive parts and motorcycle performance parts, which I'm an enthusiast or passionate about. But I'll keep sharing both the videos with you guys. Thank you, everyone.